Okay, let's do a video here about net force and equilibrium. So exciting. Okay, great. So I've got my piggy here on a leash, and I want to take my piggy for a little walk. But Piggy's being very stubborn. So I'm pulling on Piggy, but Piggy's not moving. Yes, so here we go. Pulling on Piggy, Piggy's not moving. So Piggy's digging his feet into the ground there and creating a lot of friction. So I want to actually draw a free body diagram of the Piggy. I'm going to draw him from the side perspective like this. So we're going to draw a free body diagram of the Piggy from the side perspective. Okay, so let's do that. So I'm first going to draw the Piggy as a dot. Yep, and of course, let's adjust the exposure again on this. Okay, hopefully that's good. So we got the Piggy as a dot, and one force that's almost always present for these problems is going to be gravity going down like this. And then I've also got me pulling on the rope, what's really the rope that's pulling on the Piggy. So I'm going to label that as a tension, Ft. Tension is going to go that way. Okay? Now we've got a little bit of a problem here. If these are the only forces that I'm drawing, then you'd see the Piggy would be going off in a kind of a funny direction. So I've got to balance out some forces here. So I know that the Piggy's resting on the ground, and there's going to be a force from the ground pushing up on the Piggy, right? So there's the table pushing up on Piggy from the side perspective. I'm going to draw a force going this way, and I know it's got to balance with this force over here. So that is going to be our normal force like that. And since, did I draw those pretty well? No, I guess this one probably needs to be a little bit longer, huh? Let's make this one a little bit longer. Good, so I want these two force vectors to be equal to each other, equal in length. Now I've got this tension going this way, which means I've also got a force going this way that needs to be equal in length. Boy, I'm not doing a very good job of that. There we go, that's a little bit better. So that I'm going to label as F with a little f for friction. Friction going that way. So I've got tension going this way, and I've got friction going that way. So often in physics we talk about this idea of what we call net force. And the net force is really going to be adding up all the forces, summing them together. So sometimes we write it as this, F net, like that. Or sometimes we write it as this, with a little sigma. And that little sigma means sum of the forces. You're going to add forces together. So what does that really mean? Let's just look in one particular direction here. Let's look in the up and down direction. If I'm looking for the net force in this up and down direction, I'm going to add up all the forces. Keeping in mind that when we have vectors, one thing that's going in one direction and one thing that's going in another direction, when we say we add them, it's really like subtracting them. So let's pick a direction as positive. Let's say positive is in the up direction and negative is in the down direction. So if I'm looking for in my y direction right here, y direction, if I'm looking for my net force, which I'm going to write as F net, then I'm going to write normal force minus gravity. It's really adding them together, but it's one of them is in the negative direction. So I've added my forces together just like that. If I'm going to look in the x direction, which I'm going to do over on this side, so in the x direction I've got tension and I've got friction right there. So I'm going to choose positive as to the right and negative as to the left. That's pretty conventional there. So when I write in my x direction, if I want to write what is my net force, I'm going to write F net. Then I'm going to write tension going that way, Ft minus friction going that way, Ff, like that. So this is how I've set up things that have a net force on them. I feel like everything's kind of out of focus. Maybe that's a little bit better. Okay. So this is how I would write net force, the sum of the forces. And we want to add up forces because we want to see what's happening overall. And of course, we want to keep them separated. What's happening in the vertical direction, we want to keep separate from what's happening in the horizontal direction, right? So let's talk about this concept that we call equilibrium. And I have it written out right here. So what we say is an object is in equilibrium when the vector sum, that means adding things like vectors, when the vector sum of all the forces acting on it is 0. So that would be like this situation up here. right? We have a situation where we've got the piggy and all the forces acting in the x direction add up to 0, all the forces acting in the y direction add up to 0, and this would be something that I would call it being in equilibrium. Equilibrium, when all the vector sum of all the forces acting on it are 0, and the piggy wasn't moving. There's actually two different types of equilibrium that we can talk about. We can talk about what's called static equilibrium, and we can talk about what's called dynamic equilibrium. So there's a little bit of a difference between these two things. Static equilibrium, of course, to have equilibrium in general, you need to have the sum of all the forces has to be 0 for either of these equilibrium cases. Sum of the forces equals 0. Now the word static here means not moving, and the dynamic means it is moving. So in a static equilibrium, we're going to have the velocity of the object is going to be 0, meaning it's not moving. That's just like the situation with the piggy, where I'm pulling on the piggy and the piggy's not moving at all, right? So that would be an example of static equilibrium, where the sum of the forces is 0 and the velocity is still 0. In a dynamic equilibrium situation, we would have it that the velocity is not 0. So what would that look like? That would be like if my truck right here were just driving at a nice constant speed along the ground. Let's make the truck go this way. So I'm going to draw a free body diagram of the truck moving along at a constant speed along the ground like this. All right? So here we go. And this is going to be an example of something in dynamic equilibrium. Notice how I said constant speed. That was something that was really important. So here's our free body diagram. I'm going to draw a dot, drawing it from the side perspective again, okay? So there's the side perspective. Of course, we're going to have gravity going down. We're going to have a normal force going up like that. Did I draw those equal? No. Why am I doing such a bad job of that? Okay. We're going to have something going this way. This is a situation where something's pushing this truck forward. And I would call it like the engine or something like that. It's hard to describe. It's not one of our kind of basic forces right here. So I'm going to call this like F engine or something like that. And then something slowing it down in this direction to prevent it from getting faster and faster. And that's going to be friction going like this. Okay, and these two are supposed to be equal to each other, the friction force and the engine force. So we still have a situation where in the vertical direction, we add up all those forces and it equals 0. In the horizontal direction, we add up all those forces and it equals 0. So we're still in equilibrium, which means the sum of all the forces equals 0. But the truck was actually moving. And it's a little bit of a hard conception sometimes for physics students to realize that if you have the sum of the forces equaling 0, you can still actually be moving. The key here is that your acceleration is 0 in both of these situations. You're not accelerating, meaning you're not speeding up and you're not slowing down, and you're also not changing directions. So the truck is moving along at a nice constant speed. It doesn't need a net force in order to do that. If there were a net force on it, it would start to accelerate. But while we're in equilibrium here, static or dynamic equilibrium, it means our acceleration is 0. We have 0 acceleration. Of course, if you have 0 velocity and 0 acceleration, you're not going anywhere. So that's the pig being pulled, not going anywhere, right? But you can also have 0 acceleration and still be going somewhere. It just means you're going at a constant speed. So the truck is just going at a nice constant speed right there. So there's static and dynamic equilibrium. Here's our definition of equilibrium, and we also talked about net force.